Now the next property you are going to learn is the time differentiation property, okay, or differentiation in time domain property, okay. So this property is very important, not for just only for the problems, but also for the proof also, okay. And this property we are mainly using for solving the differential equations, which you will be doing in the coming classes. In the coming videos I will be showing you how to use this property for solving differential equations, okay, and also for finding the impulse responses, okay. So this equation is more than enough. If you this equation is very important, and this equation is very important for finding the impulse responses and transfer functions of various systems, okay. So this equation has a lot of, if you just simply remember this equation, you will be covering a lot of portions in the fourth module, just simply applying these two equations, okay. So this property, it states that if the Laplace transform of x of t is equal to x of s, then the Laplace transform of the differentiation of this d by dt of x of t is equal to s into x of s minus x of 0, okay. This minus means just before the value of 0, which is approximately equal to x of 0 itself. That's what it means, in the initial value, okay. So here x of 0 means x of t when t is equal to 0, right? This is the meaning of x of 0. It's called as the initial condition, okay. And likewise the Laplace transform of d square by dt square, derivative of x of t, is equal to s square x of s minus s x of 0 minus x dash of 0 minus, where x of 0 minus, like before, it is x of t at t is equal to 0, and x of 0 minus is the differentiation of x of t at t is equal to 0, okay. This is how you can see the similarity between these two equations, okay. Here the power of the derivative is, the order of the derivative is 1, so the power over here is 1 and decreasing order. So if you have s raised to 1, then here is s raised to 0. See, it goes like that. Over here the order of the derivative is 2, so that means we start the equation with s square xs minus s into x of 0 minus x dash of 0. See, s raised to 2, s raised to 1, s raised to 0, okay. So it's easy to remember this formula. Now let's look at the proof. We start with our basic Laplace transform formula, that is L of x of t is equal to integral 0 to infinity x of t into e raised to minus st dt, okay. So now what I'm going to do is I'm going to apply my Laplace transform to the derivative of this function, okay. So Laplace transform of d by dt of x of t is equal to, so how do you find it? Simply replace x of t with d by dt of x of t. So integral 0 to infinity d by dt of x of t into e raised to minus st dt, okay. So now I want to integrate this, okay. So how do I integrate this? Is by applying this formula, this integral formula, okay. Here u and v are functions of x, another variable x is not shown here. So integral u dv is equal to uv minus integral v du, okay. So now you need to identify what is your u and what is your dv and what is your v and what is your du. You need to identify these, okay. So here let u is equal to e raised to minus st, okay. U is my e raised to minus st. So if u is my e raised to minus st, then my du is minus s into e raised to minus st, right? Because here dt is the function, so minus s into e raised to minus st. Likewise, my chosen dv is d of x of t. Therefore, my v is the integral of this, which is nothing but x of t, okay. So now, so I have identified this, so therefore I have identified this. So now I am going to substitute these values over here. So which means that that means L of d by dt of x of t is equal to square bracket, and so my u is e raised to minus st. So this is e raised to minus st. My v is x of t. So x of t uv. So e raised to minus st x of t minus integral. My v is x of t. So x of t into, and my du is minus s into e raised to minus st. So minus s e raised to minus st dt. Okay. The limit is from 0 to infinity. See, this is uv minus integral v into du. Okay. So now I'm going to, this is an integration with respect to dt, time. So this minus s is a constant, right? So minus of minus becomes plus, and I can put this s outside. So it will become e raised to minus st x of t plus s into integral x of t e raised to minus st dt. Okay, from 0 to infinity. Okay, now I'm going to apply my limit inside the square bracket. So this will become e raised to minus st x of t from 0 to infinity plus s into, the limit will become 0 to infinity x of t e raised to minus st dt. Okay, so now if I apply my infinity, if I substitute the values over here, when t becomes infinity, it becomes e raised to minus infinity, which is 0. So this will become 0 minus, and here if I put 0 over here, it will become e raised to 0 into x of 0. E raised to 0 is 1, so you will get x of 0. So 0 minus x of 0 plus s into, this is nothing but the Laplace transform of x of t, right, which is capital letter x of s. So plus x of s, or in other words, Laplace of d by dt of x of t is equal to s into x of s minus x of 0, where x of 0 is the value of x of t at t is equal to 0. Okay, this is how we apply the proof. Okay, so now if I want to find the value of this, the Laplace transform of d square by dt square x of t, if I want to find the value of this, then I simply apply the Laplace transform of its derivative of its derivative. Okay, we know that we just found out that the Laplace transform of d by dt, right, of x of t, right, is equal to s into x of s minus x of 0, right, x of 0. So this is, so if I want to find the d square by dt square of x of t, then it is the Laplace transform d of dt of this function. So I replace x of s with the Laplace of this, that is Laplace of d by dt x of t minus, then I replace this. This is what? This is the value of x of t at time t is equal to 0. Okay, so now I'm going to replace this with this, which is nothing but value of d by dt of x of t at time t is equal to 0. Okay, so this is s into, now this term is represented as x dash of 0, and the Laplace of this we have already discovered. The Laplace of this Laplace of d by dt of x of t is nothing but x into x of s minus x of 0. Okay, so multiplying the s inside, I will get this equation, s square into x of s minus x of 0 minus x dash of 0. Okay, so this property, like I said before, is very important when we are solving differential equations and when we are finding the solutions of differential equations, or when you are trying to find the impulse response or the transfer functions of these systems. In those kinds of problems, we will be simply applying these equations directly. So it's very easy to remember, and it's very important also. Okay, now the next property you are going to learn is the time integration property. Okay, this property is, the problems for this property has very few chance of asking, and more important than the problem is the derivation of this property. This derivation they have asked in the question paper. I think in around 2017 or 2018 they have asked the question, find the Laplace transform of an ideal integrator. That was the question they asked. They didn't ask this question directly. They didn't ask state and prove time integration property. They just said find the Laplace transform of an ideal integrator. An ideal integrator means an integrator which doesn't have any resistor or capacitor. That means the value of R is 1 and the value of C is 1. Okay, so in that question all you need to do is simply prove this. derive this? That's the question. Okay, so time integration property means the time is being integrated as x of t is integrated. So let's look at the statement. If Laplace transform of x of t is equal to x of s, then the Laplace transform of integral minus infinity to t x of tau d tau. Tau is a dummy variable because I have already used minus infinity to t over here. T is my time. That means I am integrating the signal from before up to time t, up to a certain time t. So I can't use t over here. So it is x of tau d tau. Tau is my dummy variable. So this is equal to x of s by s, x of s by s plus integral minus infinity to 0 x of tau d tau by s. Okay. So now let's see how the proof is done. Let another function f of t. Let f of t is equal to integral minus infinity to t x of tau d tau. Okay, let this be your first equation. F of t is equal to integral minus infinity to t x of tau d tau. Differentiating this above equation with respect to t. Okay, with respect to t. Differentiating the above equation with respect to t, we get, if I differentiate this, I'll get d by dt of f of t. Okay, and if I differentiate this is an integral, so applying differentiation to the integral, it gets cancelled, so you'll get x of t. Okay, and this is your, let this be equation number 1. Okay, now in this above equation, suppose if I put t is equal to 0, t is equal to 0, this will become f of 0 is equal to integral minus infinity to 0 x of tau d tau. That is equation number 2. Let that be equation number 2. Okay. Now next what I'm going to do is, I'm going to apply Laplace transform to my equation number 1. I'm going to apply Laplace transform to equation number 1. So what do I get? The Laplace transform of this is L of d by dt of f of t is equal to the Laplace transform of this, which is L of x of t. Okay. We have already derived this in the previous derivation, in the previous property, time differentiation property, right? D by dt of f of t is nothing but s into Laplace transform of f of t, which is f of s minus f of 0, which is the value of f of t at time t is equal to 0, is equal to Laplace of x of t is x of s. Okay. Now I'm going to rearrange these terms so that only f of s remains here. So putting over here, it will be s into f of s is equal to x of s plus f of 0 minus, and the next step, I'm going to divide this entire equation by s. It will become f of s is equal to x of s by s plus f of 0 by s. Let this be equation number 3. So what I'm going to do now is, I'm going to put this equation inside this equation. That is, here the value of f of 0 is given over here. This value I'm going to substitute over here. Okay, so substituting equation 2 to equation 3. Substituting equation 2 to equation 3, then this will become f of s is equal to x of s by s plus integral minus infinity to 0 x of tau by s d tau. See, this is f of 0. This term is f of 0. This is f of 0. So, but f of s is nothing but the Laplace transform of f of t, and I have already defined what is my f of t in the beginning. F of t is what? Integral minus infinity to t x of tau d tau. So therefore f of s is nothing but integral minus infinity to t x of tau d tau, Laplace transform of this. So this is, so therefore L of the Laplace, therefore Laplace transform of integral minus infinity to t x of tau d tau is equal to x of s by s plus 1 by s integral minus infinity to 0 x of tau d tau. That's it. See, this is how we solve this derivation. Okay. So like I said, here they have not asked that much problems from this section, from this property. Okay, here the derivation is more important than the problem itself. Okay.